Hello everyone, and welcome to the third webinar in the CERDP and ESTCP webinar series. My name is Rula Deeb. I am a principal at Geosyntec Consultants in Oakland, California, and the organizer of the webinar series on behalf of CERDP and ESTCP. I will be co-facilitating today's call. The webinar will consist of a brief overview of CERDP and ESTCP by Dr. Andrea Leeson, followed by a sneak peek at a few of the upcoming webinars in the newly launched webinar series. Following Andrea's opening remarks, we will transition to the technical portion of the webinar. This webinar features two speakers who will discuss new tools for improving the management of contaminated sediment sites. We will start with Dr. Phil Geschwind from MIT, who will give a 30-minute presentation followed by a short Q&A session. Phil will be followed by Dr. Bart Chadwick from Cporewater Systems Center Pacific, who will also give a 30-minute presentation followed by another Q&A session. We will conclude the webinar with an interactive Q&A session including both speakers. I'd like to remind everyone that today's broadcast will be listen only. This is because of the number of folks that have registered for this event. We have over 350 registrations. However, you may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions in advance of the Q&A sessions. With that number of attendees, it is logistically challenging to open all the lines for oral questions. So as a reminder, we will keep the phone lines on listen only throughout the presentation. And with that, I would like to introduce Dr. Leeson, who is the Deputy Director of CERDP and ESTCP, as well as serving as the Program Manager for the Environmental Restoration Program. Andrea has been with CERDP and ESTCP since 2001, and prior to that she was a research scientist at Battelle Memorial Institute, where she conducted research on in situ bioremediation. And with that, I turn it over to you, Andrea.
Thank you, Rula. I'm happy to welcome everyone to CERDP and ESTCP's webinar today. CERDP is the Strategic Environmental Research and Development Program, and we were established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. CERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, and here we demonstrate innovative environmental and energy technologies. These investments are intended to capitalize on past investments under CERDP or other research programs, and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs with much of CERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted for these studies also. There are 4 program areas in CERDP, 5 in ESTCP. The Energy and Water Program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapons System and Platforms, are CERDP and ESTCP programs that are managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. Under environmental restoration, we have essentially 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series will be highlighting research and demonstration efforts from each of the 5 different program areas. As you can see, our webinars will cover a broad range of topics, with upcoming topics covering waste-to-energy technologies, DNAPL source zone management, energy audits, and sustainable materials. You can find more information about upcoming webinars at this link. Registration is now live for the Energy Audits webinar and will be live shortly for the webinar on Waste to Energy Technologies. I hope you enjoy the webinar today. And Rula, I'll turn it back to you.
Thank you, Andrea. And it is my absolute pleasure to introduce Dr. Phil Geschwend from MIT. Phil is a professor in the Department of Civil and Environmental Engineering, and he is also the director of the Ralph M. Parsons Laboratory for Environmental Science and Engineering. Phil's background is in environmental organic chemistry and geochemistry, and his work focuses on investigating the fate of organic compounds in the environment. Phil received his PhD in chemical oceanography from the Woods Hole Oceanographic Institute, and prior to joining the faculty at MIT in 1981, he served as a postdoc in chemical engineering at MIT and at Indiana University in the School of Public and Environmental Affairs. And Phil will be talking to us today about passive sampling in support of remediation of contaminated sediments. And with that, I'd like to turn it over to you, Phil.
Thank you very much, Rula. Excuse me. Hello to everybody from Cambridge, Massachusetts, where, of course, the polar vortex is treating us to an early winter. I hope you're all doing well. Today what I want to do is I do want to talk about our use of passive sampling in terms of evaluating environmental systems, in particular sediments. Before I forget to do so, I have to, of course, remind myself to acknowledge a lot of people who've helped with this. In particular, John McFarland, Loretta Fernandez will develop much of the data I'll show, as did Jennifer Apell and Patricia Tachik. We also want to be thankful to colleagues at EPA, in particular Rob Burgess and Rachel Thompson, who helped us access a site where we could test some of our work. And also my colleagues Kevin Paella et al. At ICF International, who helped us with some of the work that I'll talk about today. And last but not least, of course, our funding from CERDP and ESTCP, as well as some other corresponding funding from EPA and things of that sort. Anyway, to begin, let me tell you that I'm going to tell a little bit about what I see as the problem that we're addressing. Follow that with a little bit of background information for those of you who haven't thought about it this way, how to attack the problem. And then describe a little bit about our approach of how to use a polyethylene sampler, or any passive sampler for that matter, to work on such problems. And then finally what I'll do is give 3 case studies where we've used these passive samplers to understand what's going on at these sites and try to develop a better knowledge of how to remediate, how much we need to remediate, and things of that sort. So let's begin with the problem. And it's not probably surprising to many of you that many of us are worried about a lot of different organic pollutants, polybrominated diphenyl ethers, pesticides, herbicides, steroids, all kinds of things of this sort. And many of them, unfortunately, are persistent and can accumulate in organisms, of course, and have enough toxicity that we're worried about them. And we often talk about these as hating water, i.e. being hydrophobic, but that's also a synonym for meaning they love sediments. They're sedimenophilic, if you want to call them that. So as a result, we expect these things to pile up in our sediments, and we have to think about what does that mean in terms of the risks we will enjoy from having them out there. And for sort of a point of reference, a few years ago, the EPA put out a document pointing out that something like 1/10 of all the sediments in the United States have enough of these kinds of contaminants in the sediments to pose risks to the fish that live there and the humans and wildlife that eat that fish. So it's conceivably a pretty big problem in terms of both the nature of materials we're talking about and the kinds of situations that we have all over the place. Continuing with this a little bit, the point of view that we're taking is that the risks are largely based on the concentrations that build up in the biota of interest, such as the fish. And we use various kinds of models, biota sediment accumulation factors or food web models, et cetera, to try to understand how to translate concentrations in sediments into what we would see in the corresponding fish. And that's all well and good, except for one thing. If we don't get the, quote, exposure information correct, then we don't have a very good opportunity to use those exposures to anticipate what accumulates in the organisms. Our thesis is that we really need to have something proportional to the chemical activities in these complicated sediment systems, and one metric of that is the concentration in the pore water, and that's been arrived at for now a couple of decades. And up till now, we've largely tried to estimate that parameter by using sediment concentrations and normalizing by an estimate of the sorption coefficients, that is the product of the organic carbon content, FOC, and the organic chemicals partitioning into organic carbon from water, the KOC. And we would offer that approach, that historical approach, has not been very accurate, and we could do a better job. Let me say a couple things about that, about the problem. So, for example, one particular site we've been able to use passive sampling, and I'll tell you about this a little bit later, is we've been looking at the site in San Francisco Bay that has a DDT legacy of contamination. And in the mid-1990s, many tons of sediment were removed from that site in an effort to clean it up. And things did indeed seem to get better for a short amount of time, as indicated by concentrations in mussels that live or were deployed in that area. But after several years, the mussels went back to where they came from in terms of the loads in their bodies for DDTs, causing people to scratch their heads and say, wait a minute, we just spent these millions of dollars cleaning up the site, and it's not successful with respect to biota body burdens, which is what we're interested in for understanding risks. I would offer that we need a better way to understand the source, or put it another way, we need a better way to understand the exposures, which is sort of a synonym way of saying that. So let's shift to the background. In general background purposes, I would again point to pore water concentrations as the best possible metric that we can have at this time to understand how sediments expose organisms and act as sources for these ecosystems. I would just point to one particular example of this sort that Steve Hawthorne and his colleagues published when they studied how hyella survived various kinds of sediments with different polycyclic aromatic hydrocarbon presence in the sediments. And as shown in that graphic, they find that the percent survival of the hyella is near 100% until they get to a certain amount in the pore water, which is indicated there by about 10 units of micromoles of pHs per gram of lipid correspondence. That tightening of the data set is very comforting in a sense, but it's even more comforting to me because when I see where that drop-off is, that corresponds to something like 1% of the lipid content in the organisms would have PAHs in it. And that is an amount that physiologically would be expected to be toxic. So the actual location of the effect corresponds to what we think should be the case in terms of theory. So this kind of thinking about pore water as the driver of exposure and therefore in turn causing organisms to have accumulations, which in turn is a predictable toxicity kind of effect, is I think a good strong support for why we want to have pore water as a metric of what's going on. The problem with taking sediments is that we have a lot of different materials in the complicated world of sediments in which organisms like the soft-shelled clam Maya live. You have the natural organic matter. You, of course, have the pore water. You have clays. You have another fun group of things called black carbons, sort of soots and chars and things of this sort. And all of those grab a hold of some of the chemicals of interest. And we need to understand how those interact with each other to really know what Maya feels or any other organism feels in terms of the surroundings exposures. If we could know any one phase in its concentration and then know the partitioning from that phase into the Maya, we would have this understood. The problem is it's hard to know any one phase's concentration. The one phase that we can know fairly well is the pore water concentration. So if I could know that one phase in the sediment and assume it's equilibrated with all the other phases, then I know also Maya's exposure, if you will. So that's why we argue again that we need to have this pore water information. One last way to exhibit this is to look at some data that Ryan Lohman looked at in my group several years ago, where he looked at the body burdens that we observed in soft-shelled clams living in different sediments in terms of polycyclic aromatic hydrocarbons. And he predicted what should be in the clam using this standard method of taking the sediment concentration and dividing it by this FOC-KOC estimate of KD. And when he did that for 4 different pHs, what he sees, as shown on the left here, I guess I can point to that, is that we end up seeing that the concentrations in the organisms are about a factor of 100 different than what we predicted. In fact, they're 100 times less than what we predicted. And the idea is that that's because we have an error when we do this estimation of the KD up here, or the absorption coefficient with FOC-KOC, because we don't understand or we're not including everything that holds onto the chemicals of interest to us. If we go forward and add a black carbon metric to this KD, as shown on the upper right above the second plot, we end up having some estimates of how much more sorption there is, how much greater the KD is, which will indeed lower the pore water concentrations. And when we make clam predictions in that sense, now we find that we have a sort of a noisy prediction, I admit, but still a much more accurate prediction in the vicinity of predictions being close to what we observe in the clams. So rather than focusing on the issue of precision, we're working on the issue of accuracy at this point, and we think that this is a much more accurate approach for, if you will, having a metric of what the organisms feel. So by way of background now, we have the problem that if we could know pore water, then we could go forward and do a better job of estimating risks at site, identifying sources at site, and knowing somewhat what better job to do to clean them up. So let's talk for a few minutes about the PE approach. The PE approach is largely designed to give us this pore water information that I've just tried to convince you we need to have. And the idea is to add one more phase to this complicated sediment, i.e. some polyethylene, which is a fairly simple plastic, of course, and add that to the sediment and let it sit there long enough until it accumulates the contaminants in some relation to what's in all the other phases, including the pore water. So if we can know what accumulates in the polyethylene, I'll call that C sub polyethylene or PE, we could indeed use that with a partition constant between polyethylene and water to calculate the pore water concentrations as indicated by the equation on the left there. Going forward with that, the PE method is not all that complicated. One simply goes to a hardware store and purchases a drop cloth made of polyethylene. There's a picture of some drop cloth. Instead of using it for painting the ceiling of your kitchen, we use it as a passive sampler. We cut out pieces of that polyethylene. We clean it with some solvents just to make sure that it hasn't accumulated something from people's handling of it, packaging it, shipping it, storing it. And then we add internal standards that are called PRCs, or Performance Reference Compounds, to the polyethylene. These performance reference compounds will serve to tell us when the polyethylene is deployed in the environment how close to equilibration is this polyethylene sampler to the surroundings it's in. Anyway, after we've loaded this cleaned PE with the internal standards, then we can load the strips of PE into a sampling device as pictured on the sort of right of the slide, and we can have the polyethylene in a frame. In this case, it's an aluminum sheet metal frame that we can stick into the sediments. In this particular picture, it has a pole on the top that Steve Reichenbacher put together, and the pole allows this material to be actually deployed in a lake, for example, up to 5 or 6 meters deep, say 15 feet deep, and left in the bottom until we want to come back later and pick it back up. Below the particular schematic, we have a picture of a piece of polyethylene that's just been recovered. I'll show you some more of those later. But the top part was in the bottom water, and it gets covered with a biofilm. The bottom part of the polyethylene is transparent here, and as a result of that, it's not been accumulating biofilm. But all up and down this sampler, we've been accumulating, in this case, PCBs at this lake. After about a month of deployment, we take the polyethylene back out of the lake. We wipe it clean with a chem wipe. We extract it with an organic solvent, and we analyze the extracts with GCMS. So nothing that's especially novel in that respect. In some ways, in fact, this analysis is easier than sediment analysis because you don't have all the other confounding things that accumulate in sediment extracts, such as lipids, sulfur, things of this sort, and have to take care of that material in terms of secondary cleanups in this extract. We don't do any secondary cleanups. We run the extract straight on the GCMS almost entirely. So moving on, we have now some information about how good this methodology works, and in particular, it depends a large part on the performance reference compounds, or those internal standards. So what's shown here is some data from the lake sediment, where we're looking at 2 particular PCB congeners. And what's shown in each graph is the concentration that accumulates in the polyethylene as a function of time. This is the target compound for congener 52 as we go as a function of time. At the same time as it's accumulating, a reference standard that we put in the polyethylene that is C13 labeled is leaving the polyethylene and going into the surroundings. And so we can understand how close this sampler is approached to equilibrium over time by watching how fast this compound, or to what extent this compound has left. And if we take that fractional loss or approach to equilibrium and operate on the amount that we've accumulated, we can convert this accumulated load into what we would have calculated had it had enough time to reach equilibrium. And the dashed line are independent measurements of what the equilibrium amount would have been. And what you see are the extrapolated blue data using the PRCs to estimate what it would be had we left it at infinite time. Matches quite well to what we actually see when we do a thorough analysis. So this PRC correction does a very good job of giving us what the concentration in the polyethylene would be, C infinity polyethylene, had we waited to equilibrium. And now using the known polyethylene water partition constants that we have from laboratory studies, we can use this result for the polyethylene to solve directly for the pore water. So this is a very useful and excellent way to save time by not waiting for this thing to come all the way to equilibrium. And secondly, to understand what are biofilms and rust coatings and things like that doing on the polyethylene, because the internal standard is transferring across those same films as the target compounds are transferring. So no matter what system you deploy in, the internal standards are telling you how this is operating as a function of time, temperature, coatings, and things of that sort. It's a very important approach. Moving then a little bit further, say a couple more words about accuracy. Here's some data from 2 sites in Boston Harbor area, a coal tar site at Island End, and actually a site that's used for shell fishing at Dorchester Bay. And these happen to be for polycyclic aromatic hydrocarbons. And what we did was we collected pore water, as indicated here on the sort of right axis, by centrifugation and extracting that water, having taken the colloids out of the system. And on the vertical axis, we're plotting against what the polyethylene sees in those. And what you see is a strong correlation on what we see using polyethylene to calculate what's in the pore water to what we see by directly measuring the pore water. So we have a good feeling that this methodology is working well for PAHs. And likewise, one more comparison that I want to emphasize has to do with how is this polyethylene approach compared to methods that are currently largely in practice. What we did is we spent a lot of effort in what's called an air bridge approach, which I'm happy to describe for others, to anticipate what a PCB congener would be from Hunter's Point sediment here in San Francisco Bay. And what we did was we got an air bridge result, which is in the vicinity of 1 plus or minus about half a nanogram per liter for this particular congener. If we squeeze out some pore water and analyze it, we get about a factor of 5 larger. If we make some colloid corrections, which are somewhat complicated to do, we get closer to the answer, but again, this is an extra lot of work and somewhat uncertain. If we use the current practice of extracting the sediment and dividing by an FOC-KOC estimate of KD, the answer turns out to be 32 nanograms per liter, obviously order of magnitude or more off from the air bridge result. If we try to correct for black carbon in the sediment, we can get closer, but again, it's a complicated correction. I'm not sure I necessarily want to recommend it yet until we understand more about how this works. But if we use polyethylene deployed in the sediment, we get results right off the bat with the error bars there, which are corresponding to in the order of a nanogram per liter for this congener, and it applies to the other larger congeners too. So once again, relative to current practice, what we think is that these passive samplers deployed in these environments, again, here's a passive sampler, when you bring them up out of the environment and analyze what it accumulates and normalize it, correcting it with the performance reference compounds and normalizing it by the polyethylene water partition constants, we do a much better job of estimating the pore water, that is the exposure the organisms feel, the pore water, the amount that drives transport from the sediment bed to the overlying water, the value we need to know for understanding these kinds of sites. So with that, I'd like to talk briefly about 3 case studies and what some of the kinds of things we've been able to do with this kind of data. The first case study is a simple one here in Boston. It was done by Loretta Fernandez, and what she did is she walked out to these 6 locations along the shore here of Boston where there are Maya, soft-shelled clams living in the bed. You can, of course, see where their siphon hole is near the bed. And when she would see siphon holes, she would deploy passive samplers near to these sites, be it in the South Dorchester Bay, at the Island End site, up here in Saugus and Salem where there's coal-fired power plants. And what she would do is leave those samplers in place for a week, come back, pick them up, pick up the clam they were living next to, analyze what's in the clam, which is on the y-axis here, analyze what's inferred to be in the pore water from the polyethylene, and except for one goofy point, all the rest look quite good with respect to error that we have in our analyses and things of that sort in a one-to-one line. So the idea is that the passive samplers are doing a very good job of understanding what's accumulating in this particular soft-shell clam biota that we're interested in. Case study number 2. We have the site I mentioned earlier in San Francisco Bay where there is a DDT problem in this area of the bay in this channel. And so we wanted to understand what is this accuracy of a conceptual model that the main source of the DDT in the water column is diffusing up out of the bed, and therefore fixing the bed is the main problem. And secondarily, we wanted to test the idea that could these passive samplers actually work as well as the biomonitors that are constantly deployed. They're the mussels. So in order to test those 2 ideas, we did the following. We deployed polyethylene samplers down the channel. That's what's indicated here on the right in the sort of graphic. And what we see when we deploy the passive samplers for about a month, pull them up, is we see concentrations in the water in this particular station in the very north at C1800. We have a blue value there, which is the water concentration of DDD in this particular case, 4,4 DDD. In the bottom water, it happens to be about 150 nanograms per liter concentration, very high. And when we look in the sediment, we end up seeing a much higher number. That's the browner number. It's about 1,300 nanograms per liter. As we go down the channel, these concentrations fall off, thankfully. As you get to a background site, shown over here on the bottom right, it's much, much less, so it's not something in the background that we're seeing. So consequently, this channel obviously is showing elevated pore water concentrations, especially in its northern extent. And most importantly, with these two numbers, something in the bottom water, something in the upper pore water, we can start to think about calculating bed water fluxes of this kind of a chemical and asking, are those fluxes sufficient to explain what we see in the overlying waters and cause the accumulations in the fish and the shellfish? So in this graphic, all I'm showing is starting in the north here on the right and going out of the channel. We can calculate fluxes for individual compounds like the 4,4-DDD, 4,4-DDE, 4,4-DDT, and they generally fall off as you go toward the mouth of the channel, and the values of the fluxes are shown there. Notice it's on a log scale, so this relatively shallow change here is actually quite steep. It's orders of magnitude change as you go down the channel. Using that information, we can now put those fluxes in a conceptual model that says the sediments, here as indicated by these red bars, are the main source of the DDTs to this water column. And the main sink is the tidal flushing. Water goes in and out, and as such, when the tide comes in, water is coming in and picking up DDT as it goes over these fluxing sediment beds. And as the sediment water column gets mixed, then the tides reverse and take the DDT back out the other side. So we have a balance in a hypothesis sense between what's fluxing out of the bottom versus what's being flushed out by the tide. If the bottom sediments are the source, which we can know from the PE data, then we should see a balance that way. In order to test this idea, we went and deployed polyethylene in the water column, not just the bed. And these are two different campaigns, field campaigns where this happened. Each different colored point is a different DDT congener or degradate. And what we have on the x-axis is what we anticipate in the water from the mussels that were deployed, and on the y-axis is what we see when we use the polyethylene and correct the data with the PRCs. Interestingly, at one time of year on the right here, we actually have very, very strong correspondence between what's in the mussels and what's in the PE. And it was a relatively quiescent time of year. A little bit later, there was a lot of tugboat activity, so there's a certain amount of resuspension going on, and we suspect that the mussels are getting an extra dose from resuspension. But in both cases, there's a strong correlation between what the passive sampler and what the mussel says is in the water column. Using these kinds of data now to see what we know is in the water column, we can compare it with what the model I showed on the previous slide says should be in the water column. And I just briefly point to some outputs of this, where I show you the ratio of what we see in the water in the denominator versus what we model in the water from that simple tidal flushing versus diffusion out of the bed model. What we see is no matter what games we play with the bottom boundary layer, flushing tidal rate, things of this sort, we can't balance the ratios in the northern end of the channel. These numbers optimally want to be ratio 1, that is model equals measure, and with keeping the ratios okay at the southern end of the channel. These numbers are far below 1. I can increase fluxes out of the bed by shrinking bottom boundary layers and play games like that. That's what's happening with these numbers here. It's a bunch of fitting that's going on to try to balance what we see in the water with what we think is going on from the sediments, knowing the passive sampling data. And there's no simple way to do this by simply changing boundary layers, knowing tides, things of this sort. In fact, the only way you can balance this kind of thing is to say there has to be some kind of extra input here in the mid-channel, which would elevate these concentrations in the southern part of the channel to what we actually see compared to what we model. So we're missing a source. And simultaneously with this, my colleagues from CH2M Hill and Sea Engineering were looking at the same site and seeing that there's another hydrology plume coming off the site, which is probably at about this location in the channel, which seems to explain some of what we're not understanding by simply using the passive sampler. So the data are working together to understand the conceptual model of the site. One last point about this use of passive sampling has to do with a case study that is involved in a lake here in New England, and it has a PCB contamination in the lake. We wanted to understand a little bit better what's going on with the initial views in the food web, that's where the chemicals are accumulating is from that point of view. Wanted to see how well we could map the site. And we found out by accident, if you will, because we're looking in the site, something about whether and how the site operates, which is important to biota exposures. So coming back to that, when we first arrived and started looking at the site, this is what was known. No one could detect the concentrations in the water column. Concentrations were found in the sediment. They were therefore inferred to be the problem. and of course concentrations were seen in benthic organisms and in fish. And we wanted to understand how these are connected to each other, and there are various models for that, but we speculate that the concentration that would be estimated from the pore water using the sea sediment information would not be very useful. So what we did is, of course, we applied passive sampling at this site, and we repeated the observations. And now by using the passive sampling data, which is the information on the right-hand column here, we do see readily the concentrations of specific congeners in the water column. So congener 52 happens to be at 10 picograms per liter using our passive sampling information, the PRC data, and the polyethylene water partition constants. That number looks very much like the small organisms, like the perch that live in this area. So that's a good sense of what's going on. And using the passive samplers in the pore water, we see that we expect about a 400 picogram per liter of this kind of congener in the pore water, as contrasted with the current practice would have expected 5,000. This number 400 is more in line with dosing between 10 in the water column and 400 in the bottom water, and explains more what we see in higher trophic levels and, in fact, organisms that live in the bottom water, who are, of course, balanced between this breathing water and this water they're immersed in. So we think that this kind of thing, when fed into food web models, will do a much better job than using the 5,000 kind of number to understand the doses of these organisms. Second aspect of the problem is, could we map it? What's shown in the middle is what the contractors at ICF and others had found for where the hot spots were in the green here in this area using sediment data. So much of the remedial design is based on removing these high sediment concentrations. When we repeated the exercise and tried to use this kind of KD with FOC, KOC, we start to see a hint of a different thing, partly because we were willing to go into the sediment sites very near the shore, which were not typically looked at by sediment sampling. These near-shore samplers tend to be very sandy, and were never thought to have much organic matter in them, of course, so therefore no accumulation of PCBs. When we repeat the exercise using the polyethylene over here on the far right, what we see are very clear hot spots along the shore where there are very high PCB concentrations in the pore water. Since they're sandy, no one thought about these sites, no one sampled these sites, no one thought about remediating these sites. We think the pore water metric is a much better feeling for what the dosing of the organisms living in this lake system are. And we have to think in this particular case, in a surprising way, about some of the sandier sites, not just the high organic carbon content sites, which they historically thought about. Continuing, last point, we took the trouble of bringing the sediments home. That's referred to as ex situ sampling, and analyzing what's in the pore water at home. And again, here's a spread of data for numerous samples from that lake as compared to what we would get by using the sediment concentrations and normalizing by FOC, KOC. The pore water from the polyethylene estimates are much lower, about an order of magnitude lower than what we get by using the sediments, bringing everybody back home and analyzing it there. But what's really interesting is if you use the polyethylene in the field. Here are the data for the polyethylene in the field for the same kinds of sites. And what you see is that they are substantially lower than the polyethylene that we get in bringing the samples home. What that, I think, is telling us is that, of course, in the field there are other things going on that we don't get when we bring things home and let them sit around a week before we get to analyzing the pore water, such as we suspect that there's pore water flushing going on at this site. And in fact, when we start to look at that hypothesis, what we see is there are water supply wells located between 1 and 2 kilometers away, and their cone of influence seems to be affecting this site. Secondly, we see thermal anomalies going into the pore water, essentially advecting down into the pore water, depending on the season, indicating that the lake water is infiltrating. And third, we see that there's a fractionation of the PCB congeners themselves, where the smallest congeners, the most water-soluble ones, are penetrating into the bed faster than the less soluble ones. All of these things indicating that lake water is penetrating into this site. And when we do in situ PE sampling, we can see that. When we do ex situ bring the samples home sampling, we can't see that. So consequently, now I think we have a better feeling for what the doses of the organisms are that live in this part of the world, which in turn should drive more accurate food web models in effect. So with that, I want to just wrap up with something that Kevin Paella in particular helped with at ICF International. He accumulated all the expenditures that we had to accumulate by doing traditional sampling with a Ponar dredge, catching the sediment, bringing the sediment home, sending it to contract labs for analysis, and for 12 samplers, cost about $13,000. repeating the calculation for what he did with his group, not my group, with contractors using PE sampling, the bottom line was about $13,000. You end up saving money in the field work, ironically, and costing a little bit money because you have the PRCs that you have to purchase in the laboratory contract analysis. But the net result is the cost about the same. So very interestingly, the use of polyethylene samplers appears to give you more accurate results for the same amount of money, which I think is a very good result. So to summarize, we think these things are more accurate than the traditional use of sediment data. Second, we think they're very good for mapping, and in particular enabling us to see where the risks are located at a site of interest to us. We think the information is very useful for deploying it in site modeling under studies such as mass balances to understand what the main sources seem to be. Is it the sediments or something else? And last but not least, I don't think there's anything that can stop us from saying they're pretty easy to use and they're certainly safe to use. There's just a sheet of polyethylene after all. So with that, I'll quit, and I'll be happy to take any questions. And, of course, there's more information here at the CERDIP ESTC website where we have SOPs and soon to have a PRC calculator that would be helpful to people using this kind of material. Thank you all for listening. I'm happy to take questions.
Thank you, Phil, for a very interesting presentation. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We did receive around 10 questions, Phil, so I'm going to work my way through them here. For starters, have these passive samplers been commercialized, and how can interested parties access them? Also, is there regulatory acceptance of this tool at this point in time?
Right. Those are two great questions. In terms of contract labs picking up the passive samplers, we have been working with various companies, both to cause them to work with the data, but also to start to generate the passive samplers themselves. So, for example, at the current time, Lewis Berger has worked with these passive samplers at an East Coast site. They prepared the samplers. They loaded the PRCs. They deployed the samplers. They had the samplers analyzed by Axis, and the data have then been processed by the people at Lewis Berger and interacted with their regulators. I believe that they're Army Corps of Engineers for that particular site. And consequently, the data were well received and generated by that company all by itself, with us happily coaching them. In parallel, there's currently an effort, for example, on the West Coast where this is being done with ALS. And previously, we worked with, as I said before, CH2M Hill and the EPA Region 9 people at the San Francisco Bay site getting onto this regulatory acceptance part. The regulators, happy to look at the data, made more sense to them. It was a piece of a weight of evidence for example, there was a missing source that we hadn't taken care of. And so consequently, by having this more information, I think the regulators are happily starting to say, yes, we can find the sources better, as happened both on the East Coast site done by Lewis Berger and as being done on the West Coast site as done by H2H Hill and their subcontractors. And so I think it's starting to be accepted. The last but not least hard part is, how do we end up with some kind of a sediment criterion, if you want, a benchmark, some level of pollution that we can say, yes, that's too much, no, that's not good enough. That's still, I think, in process. One can argue you can use water standards because we're generating water data, but I don't know how many regulators would accept that at this point. Great.
Thank you, Phil. What about the size and details of the sensors and samplers used? Is this information readily available in your report, and can we direct the audience to where they can get this information, please?
Sure. So if you go to the website as indicated here on this last slide, there are 3 standard operating procedures published on the bottom of that site that anyone can access. And they tell you, number 1, how to prepare such a sampler, how big of a piece of sampler, things of that sort. Second, they tell you how to deploy it. And third, they tell you once you've recovered it, how to analyze it. So you have 3 sets of things. They're set up very comparable to most EPA method descriptors where they give all those pieces of information. In general, bottom line is, depends a little bit on what you're interested in. We tend to use pieces of samplers that are, if you will, 1 mil thick polyethylene, 25 micrometers. We tend to use widths that are in the order of 10 centimeters and thicknesses or heights, if you want, of order 5 centimeters. So we have approximately 50 to 100 milligram pieces of polyethylene that we process. You can slice them, of course. I didn't take time to show that. You can slice them as a function of depth into the bed and understand how far into the bed your problems are existing. But you're right, most of that stuff is already available on that website in the SOPs, if that helps answer the question quickly.
Yes, thank you so much, Phil. There's a question that has to do with the range of contaminants that the passive samplers could be used for. One question is specific to metals. Do these samplers work for metals?
That's another good question. So these samplers, because we're using polyethylene as the accumulating material, are designed to capture hydrophobic chemicals that like to dissolve into essentially hydrocarbons. Polyethylene is effectively a large hydrocarbon, a non-ionic material. It would be like using hexane as your solvent. Metals, of course, are not very happily going into such non-ionic materials. So instead, you should be thinking about a different kind of a passive sampler. And there's a group of people who, not including us, who work on such things called DGTs. And what effectively is set up is a gel through which ionic materials can diffuse. And when they arrive on the other side, there are things like resins, which can act as an infinite sink and soak up the arriving materials. Mercury is a famous one right now. So those kinds of things are being developed by other people, and I think they will essentially work the same way, but they're not quite as far along at this time.
Thank you, Phil. We have a number of questions about deploying these passive samplers. How does one know the depth to which the sampler should be deployed?
Well, you have to know something about your site, I suppose. What we do, by the way, I want to go back a step. We deploy them in a large range of ways, depending on the site of interest. So if we're doing coastal sediments that are tidally exposed, you can just walk out and stick it in the sediment all by hand, of course. We deploy them in places that are order 15, 20 feet deep from boats using this pole mechanism that I had a little cartoon of from Steve Reichenbacher at ICF. And then we use divers at sort of middling depths, 50 feet up to, say, 50-foot depths. And then we have lastly, you have a frame that's a square weighted frame that we can load the passive samplers on and drop the frame into the bottom. Recently working with Bill Jaworski in Seattle, that frame has been deployed and we put 40 samplers on in a couple of days very easily. We can insert them to a depth of interest. So really what we do is we ask the question, what kind of data do we want? Most sites, I want to know is what are the organisms exposed to. So I'm knowing those organisms, I know that if I'm talking about certain places that have 10 centimeter depth benthos, then I'm deploying to a little deeper than 10 centimeters. If I'm working in Long Island Sound and I might care about a meter of depth, then I would potentially go much deeper with my passive sampler insertion. And I want to emphasize one last part. We'd like to leave a piece of the passive sampler left above the bed so I know what's going on in the bottom water also. I think those two pieces of information, the bottom water and the uppermost pore water, are very important for understanding many of these sites.
Thank you so much, Phil. Other related deployment questions. Do these samplers need to be placed perpendicular to the flow of water, more like a barrier instead of diffusive matrix?
That's an interesting question. We actually tend to deploy them so that they're cutting directly into the flow, so that the flow has less chance to, if you want, move sediments around them by generating turbulence. So if, for example, we're deploying them in a tidal river, we will have the face of the sampler aimed at the shore, and the flow cuts across the narrow part, if you want, of the frame, generating as little turbulence as possible. Mostly that's because we are interested in having the passive sampler not change its surroundings and optimizing the likelihood it will have not been flushed away in the month or two that we leave it deployed in the field.
Thank you so much.
There have been instances. Let me add one more thing, Rula, that just occurred to me. I can think of at least one instance I know of where passive samplers put in a river were essentially washed away during a very, very strong hydrologic event. And that has something to do with, of course, this deployment angle and the nature of the flux of water across these things. You can erode them out if you are in the wrong place at the wrong time.
Thank you so much, Phil. Two more questions before we move on to our next speaker. What radius of pore water around the sampler is believed to be represented by the PE concentration?
Yeah, another great question. Depends, of course, on the chemical of interest, but to give a sense of it, This is mostly interacting with the pore water in the order of a few millimeters away from the passive sampler. Of course, the longer you leave it in place, the further out the diffusive depletion occurs. But depending on if you're PAHs or PCBs, typical kinds of contaminants we've worked with so far, we're only talking order of 5 millimeters away from the surface.
Great. Can you actually talk a little bit about the PRC loading onto the PE, or the time to load, and how exactly the PRC corrections are done?
Right. So loading is an interesting option because there's two ways you can do it. Option number one is the one I prefer, is that we take a large volume of water, which has the PRCs dissolved in it already, and we add a known mass of polyethylene, and we leave that all sealed up for a couple of months. We allow the polyethylene essentially to absorb almost all of the PRCs that we bought and put into the water. In so doing, we essentially know, because we know what we put in the water to start with, we know the mass of PRC that's accumulated in some known mass of PE. We practically know the answer. We always check that by taking pieces of that PE, extracting it and analyzing, and make sure that worked correctly. The downside of that approach is it takes a couple of months. The second approach, which is one that Booj and others in Netherlands put together, is that they work with a methanol water mixture, which of course swells the polyethylene to some extent. They find that that can load the PRCs in about a week's time, and so you save a lot of time getting ready for the next sampling exercise. The downside is you have to go through you have to use larger quantities of PRCs, which are expensive because the partitioning from the methanol water is much, much less than just from water by itself. So you don't get all of the PRC translated into the polyethylene. Maybe you only get 10%. But it only takes you a week to get that done. So again, you know something from the polyethylene water or the polyethylene methanol water partitioning, how much you're going to end up with, and you can design your samplers to have an amount of PRC which is comparable to the amount of target you think you'll accumulate. That's an important thing at the end, because you would love to run the GCMS one time and have the peak heights of the PRCs be in the same vicinity as the peak heights of the target compounds. Otherwise, you have to run twice to get both analyses done, if you will. So you want to know what your sites likely have. You want to load the PRCs at about that level using either water or methanol water, depending on how much time you have to load up your PRCs and how much money you have to spend on PRCs. And then consequently, you can have a known subset of material to work with that you should check by doing independent analyses of the product before you actually are deploying it. I don't know if I got everything in your question. Let's see.
You did, and this is
okay.
Amazing, and we're very grateful again that you agreed to give this presentation. We have 14 more questions that have come in, so we're going to wait till the end of the webinar to try and go through them. So we ask our audience to be patient, but we're going to go ahead and transition to our second speaker in the series, who is Dr. Bart Chadwick. Bart earned his PhD in oceanography from Scripps Institution of Oceanography at the University of California in San Diego. Bart currently directs research and business development for the U.S. Navy's Energy and Environmental Sciences Group at Power Systems Center Pacific. He manages a portfolio of emerging energy and environmental projects and has served as a PI on a number of high visibility projects supported by CERDUP and ESTCP. Bart, we're very happy to have you, and we're very anxious to hear about your work, so please proceed.
Thank you, Rula. I'll start off just say, along with having to get up early today, the temperatures here in San Diego dropped down into the high 50s, and I had to commute through about 3 miles of bright sunshine. So it was I know I have everyone's sympathy.
Rub it in.
Before I get started, I'll just acknowledge a couple people. I have a slide in the back with kind of more full details, but my colleague Ernie Arias, who really was instrumental in a lot of this work, both the field work and the processing of the data, and John Radford at Zebra Tech, who built really all the kind of commercial equipment for this. And then we had a couple of student teams from University of California, San Diego, that helped a lot in the early prototyping of this equipment. So what I'm going to talk about is this in situ friction sound probe. And the idea of it is really just to provide a kind of a simple tool for rapidly mapping particle size at contaminated sediment sites. So let me see, hold on a second. There we go. So just in terms of an agenda, I'm going to go through a little bit of a background on where this idea comes from, and then some description of the actual equipment, some testing we did in the lab to see if it really worked, and then 3 field applications at some different DoD sites where we tried it out in kind of different modes and applications, and then just summarize that. Then here in the photo, these are some of the UCSD students playing around with the prototype on our beach there. So the thing about particle size is really it's kind of a fundamental parameter for sediment sites. DoD, Phil kind of described, there's a broad range of these sites, not just for DoD, but for everyone across the country. A lot of these sites, we have the contamination preferentially partitioning into fine-grained particles. So you can see kind of examples of those kind of correlations over here on the right for copper and nickel and zinc, all increasing in concentration as a function of the percent of fine sediments at this site. The other thing is at groundwater surface water interaction type sites, a lot of times the groundwater is moving through more coarse-grained, permeable sediments, and so understanding grain size at those kind of sites can also be useful. And then finally, the application of this to things like capping and things can be useful in terms of profiling the thickness of caps, looking at mixing, and also looking at new deposition and things like that. So most people are familiar with the traditional methods for particle size analysis, and these usually involve collecting grabs and cores and just analyzing those by putting them through sieves or settling them through columns and then weighing the various fractions that come through that. Really requires, field collection, manipulation, handling, shipping, analysis. It's relatively tedious and time-consuming, somewhat costly, and really just precludes the kind of adaptive sampling you'd like to be able to do by having real-time data at the site as you're out there. These photos just show kind of traditional kind of sectioning of cores to get the samples you need, and then the sieving process in the laboratory. At the other end of the kind of quantitative spectrum, there's more qualitative methods that people have used. These are usually called just sediment probing, where you just take a rod and push it down into the bottom, and by feeling the response of that rod as you push it in, you can get some sense of the type of sediment and the thickness of sediment. And we've also, in this Trident probe that we use for doing groundwater surface water studies, we've done this a lot, where just using the push feel, you can kind of get a sense of the bottom type. So with friction probe technology, what we're really trying to do then is take that sort of simple idea of a push probe like that and make it somewhat more quantitative by capturing quantifying that feel in something that can be translated into something more related to particle size. So the basic idea of this then is that as you push a probe into the bottom like that, excuse me, you're displacing material out of the probe, and that's what generates this friction sound. And the friction sound then turns out to be essentially, with some assumptions about other things being constant proportional to the radius of the particles that are dragging along the probe and the length of the groove that they make in the probe. And so some early work by Ron Koumans and his group looked at this for a system where they basically had a sled they were dragging along the bottom to look at gamma detection, and they had a microphone in the sled to see if the sled was on the bottom or not. And as they dragged this thing around for miles and miles, they started to notice that the sound coming out of that microphone changed as they drug it over different types of bottoms. And so this plot here shows some work they did kind of trying to calibrate that then to grain size. And what they found was that essentially the grain size was proportional to the sound intensity coming off of this microphone. And it really changed primarily just depending on how fast they drug it. So as you drag it faster, you're getting more sound, and as you drag it slower, you get less sound. So from that idea, if you can get this sound intensity off of a probe like that, and you can control the speed at which you push it through the sediment, you can get at least a reasonably quantitative idea of the mean grain size. So here's some photos of the actual probe. Over here on the left side, you can see the probe is sort of the top of it where we have the sound cable connection and the interface to the drive system. At the tip is this the actual friction sound sensor, which is just a stainless steel tip with a microphone embedded in it. There's a sound isolator section, and then just the drive part of the probe that allows it to get deep down into the sediments. That interfaces to just a small electronics interface that digitizes the sound data, does some filtering, and then sends it out to a software interface where you can watch what's going on with the probe as you deploy it. So then the other part of this, so that's sort of the sound pickup part of the probe. And then the other part is just a part to give us that ability to make the probe go down at a constant velocity. So this is the drive system, which is essentially just a pneumatic drive cylinder mounted up here on the top of the frame. The probe then mounts to the bottom of that drive cylinder, and the rest of this frame is essentially to support the thing above the sediment until you're ready to push it in. Between the drive system and the probe, there's some other sound isolators, and then on the bottom of these legs, there's some reaction weight canisters that keep this frame from getting pushed up into the water when the probe goes into the bottom. So we built that probe, and before we took it out to the field, we just did some fairly straightforward lab tests where we pushed the probe into buckets of sort of standard sediments of different mean sizes. And so these were pushes down to about 25 centimeters in these buckets. We would repeat them over and over again in different parts of the buckets and different buckets, and in sediments ranging from clays up to fairly coarse sands. And you can see what the data looks like here on the right side. So this is for a sample of just pure clay, and you're looking on the vertical scale is depth. This point here is the interface where it hits the sediment, and then on the X scale here is the friction sound response just in sound intensity. So you can see even in a very fine clay we can distinguish the signal. It's quite low. We're getting about 2 units of sound intensity. As we move over here to this fine sand, you can see also where we hit the interface. And then now we're seeing signals up around 300 and also clearly distinctive and a nice profile there. So if you look at that response over the wide range of standards that we ran, you get a nice near linear response for clay sizes all the way up to coarse sands over about 3 orders of magnitude in size range, with kind of this expected increase in the friction sound intensity. So it's a little bit hard to see, but there's a clay sample all the way down here at the very bottom, and then getting up into the coarse sand range up here at the top of the scale. Another thing we tried in the lab, because we were interested in things like caps and being able to profile through different kinds of sediment, was we just created some layered sediments with different types of sand in those same buckets. So here's a 2-layer stratified sample where again we did replicate pushes, and this is then data that's been calibrated to those standards. So here's the probe coming down, hits the interface, and now going through very fine sand. We get the profile through that, and then hitting the interface to this coarser sand, and you can see we are able to distinguish these layers pretty nicely, and they fall into the expected range of sound response based on our calibrations and the nominal sizes of those sediment samples. So based on having a pretty good feeling for the thing working in those lab tests, we took it out and did 3 field demonstrations. The first demonstration was at Naval Base San Diego at a place called Choice Creek, which is just sort of an urban creek that runs through San Diego and empties out at the naval base. And it's a TMDL site where they're working on controlling sources and also cleaning up the sediments at this the mouth of this urban creek. So it's sort of a traditional kind of contaminated sediment site. The second demonstration we did was at Naval Base Coronado, a place called Site 9, which is a groundwater surface water interaction site where there is some potential for VOCs discharging into the surface water at this site from an upland site. So this was a demonstration where we were trying to get a sense of if we could see something about the lithology out at the interface that might be influencing where those VOCs were discharging. And then the third site was near the Washington Navy Yard on the Anacostia River pilot capping site that Danny Ribel managed. That it's a thin layer capping site where there was already a cap in place where we could go and profile through that cap and sort of test the ability to see the thickness of the cap and the mixing of the cap with native and new deposition sediments. So this is just a little bit more detail on the Choice Creek site. Essentially, I mentioned contaminated sediments at the mouth of this creek. The creek flows down from here and into this channel and then out into the bay. These are piers over here at the naval base and up here at neighboring shipyards. There's primary drivers in this are pesticides and also some metals and PAHs. And if you look at these maps, this is kind of traditional of what we see. This is a map of percent fines, and you can see right where the creek comes out, there's fairly high predominance of fines in kind of the 78-80% range. There's an area here that's scoured out, and a lot of this is related to the testing of ships over here where they do propeller tests, and it scours off the fine particles. And then finer region of particles out here in the bay again as well. And then if you look at, for instance, the total chloridane, it correlates pretty well to that pattern. So most of the chloridane, it's one of these hydrophobics, is partitioned into this fine grain material. So its pattern really is reflected in the same pattern as the fine sediments. So what we did out here, there'd been this previous TMDL work that I just showed you some of the results for 14 stations, and we went out and reoccupied 14 of those those same stations, and then also another 9 intermediate stations. We profiled with the friction probe to about 20 inches below the sediment interface, and we took cores directly adjacent to those push locations. So in other words, we would put the probe down onto the bottom, do the push, bring the probe back into the frame, and then the diver would go, and right below where the push had been done, he would take a core from there. We took the top 6 inches of those because we were mostly focusing on the surface sediments in this study, and homogenized those, subsampled and ran traditional particle size analysis. And then we also averaged the friction probe data over that same 6-inch profile, just compared the results. This map here shows just the map of the locations then where all those samples were taken. So here's some results from that. The first thing you see, these profiles up at the top are a transect essentially running from the outer creek out here through stations that run through and into the inner creek. And so you can see the low friction sound signal in the outer creek going into this coarser grain zone in that scour area, and then into very fine materials in the inner creek area. So using essentially the diver collected cores, we applied a site-specific calibration to these data and remapped the data. And you see here on the right side that map, which is essentially mean particle size, going from sort of this greenish, which is silt size and below, up into bands of different sand sizes, and then compared to the distribution from the original mapping back in the early 2000s. And those patterns still look fairly similar as they did in the original analysis, and there's quite a good correspondence between the early data and these data. So the second demonstration then was at this groundwater site, Site 9. And this is a site, as I mentioned, where there were VOCs potentially discharging to the bay. The site is on the kind of the west side of North Island Naval Air Station here. You zoom in, this pier is right around the site, essentially. So there was an old landfill up here where solvents were disposed and got into the groundwater. They're migrating towards the bay in this direction. And some previous work that we've done showed VOCs discharging into the bay, kind of in this area around the pier. These are samples taken in the Porewater down about 5 feet below the sediment water interface. So in this case, we went out and we're mapping and kind of looking for the variation in coarse and fine-grained sediments to see if there's we can gain some insight into where the VOCs are discharging and if that's related to the texture of the bottom sediments. So we went out, we mapped this whole area with about 116 stations, collected validation cores at 27 of those stations, and then averaged profiles over about 6-inch strata going down into 4 depth contours. So here's results from that mapping, starting with the deepest map on the left, the shallowest map on the left. So this is the 0 to 6-inch strata. And what we found essentially was that there's coarse-grained materials up along the shoreline is kind of like a beach essentially, transitioning into fine-grained particles around the pier in certain areas, and then offshore getting coarser into kind of the sand range again. And you can see this is sort of the mean particle size scale over here. This area that is coarser here we think corresponds to, again, where the ships tie up, and this tends to get scoured out more in this area. as you move up through these strata, the 6 to 12 inch, or down, I'm sorry, down through these strata, 6 to 12 inch, 12 to 18, 18 to 24, what you see is this fine sediment lens kind of dissipates, and you get down into sandier materials down below. And so there's essentially a lens of fine-grained material around the pier that's over top of mostly sandy materials down below. And so what we found from this, and it's getting kind of borne out by more recent data, is it suggests that there's preferential pathways both inshore and offshore of the pier. And this is playing out in data we're seeing where the VOCs we're finding are primarily either on the inside of this, and those VOCs seem to be more related to shallow groundwater. And then VOCs that we're seeing offshore here in this outer area, which appear to be more related to deeper groundwater. And we don't really see much in this area of this finer lens, which seems to be inhibiting. So the VOCs are either emerging inshore or offshore of this finer grain lens. So then the third demo we did was at the Anacostia River pilot cap site. And it's a site where there were both reactive caps and some thin layer sand caps, and also some control areas that were laid down and studied over a number of years. So we just took advantage of that to go back and see how the probe would work in going through this thin sand cap. And so this is the site on the Anacostia River. It's just downriver of the Navy Yard there. And the site was laid out with these different reactive caps, Coke Breeze, Appetite, Aqua Block, and then this thin sand cap was at the most upriver site, I believe. And then there was a control area out here further into the river. This is just a map that was made at the time those were laid down, 1 month after being laid down. You can kind of see the sand cap up here in the bathymetry. So what we did at this site, we went out and profiled 24 stations through that sand cap, including 12 stations on the cap and 12 off the cap. And we collected validation cores again at about 11 on cap and 2 off cap stations. Those cores were then segmented at regular intervals for analysis, and then of course with the friction probe we're getting sort of down around centimeter kind of resolution. So we sort of compared those profiles to see if we could distinguish the cap. So here's just working out on the river there, doing the deployment. These deployments, you drop this thing down. Doing a profile really lasts just a few minutes. So mapping these 24 stations is mostly a matter of just the time of moving the boat around. But it's on the order of hours to do this. It takes a little longer if you have a diver and you're collecting cores and things like that. So this is typical of the cores we were seeing there. So this is the top end of the core up at this end, and then the bottom of the core. And what you're seeing here is some new deposition material mixing with the top of the core, the really quite clean sand cap, and really quite good integrity of that cap still. And then the native sediments down below that. So this is sort of typical of what we got from the cores. And then this map just shows where we collected the friction probe data across the cap. And I'm going to show you a transect that kind of runs across this part of the cap in this next slide. So this is what those profiles looked like, starting from the inshore at Station 1, going offshore to Station 8. And as we march in, you see the profile of the friction probe data. This has now been calibrated into mean grain size, really very down in this very fine range. And it stays for those first 2 stations until we step onto the cap. And then the cap, we just made sort of an arbitrary cutoff here at about 300 microns mean, but you can see there's this sort of surface mixed layer of the new deposition, the integrity of the cap kind of coming down through here to about 50 centimeters, and then kind of again sort of a mixed layer going down into the native sediments. And you can see then we can get a rough idea of the thickness of the cap by doing this as we march across the cap at different locations. And there is some variability, but in general it's sort of in the range of going from 30 to 50 centimeters thick. A little bit of sand, maybe spillage off the cap on the outboard side towards the river, and then back kind of into just the native material further offshore. So we clearly can distinguish the cap and its thickness. There seems to be minimal cap material detected off the cap, even coming back. This is sort of years after the cap has been deployed. And it also illustrates these mixed layers and the new deposition that we're seeing on top of the cap. Now here's just a map then of the thickness that we detected, just to kind of give a sense of how that can map. So these dark blue dots are the off-cap locations, and they pretty much confirm no cap material except for some thin sand detected in just this southern part of the cap. And then you can see the variability of the cap thickness across the cap, but it's pretty much in the 10 to 20 inch range, which for the target was I think 12 inches for this cap. So it still looks like it's pretty much intact and in the place where it was put. So from those three demonstrations, then we took an overall look at the friction sound probe performance just by combining the data sets. This is data essentially spanned mean particle sizes ranging from the low end of the silt range up into kind of coarse sand range, especially in those cap sediments, a lot of coarse grain sands. So we didn't have anything all the way down in the actual they had a mean size in the clay range, but we had very fine silts. And so you can see the correlation here. It's pretty good, and you can see the span of these different ranges. We use this data then to evaluate performance based on a few different metrics. We looked at performance based on reliability, efficiency, and specificity, which are defined here. Reliability just being sort of a measurement of the percent that were classified correctly in those different ranges I just showed out of the total. The efficiency being the percent that were correct out of the total predicted for that class, and the specificity being the percent correct out of the total stations that were actually in that class. So you can read through this table. I won't go through it in depth, but we're targeting to try to get to about 80% in each of these performance metrics, and we pretty much met that across the board. Everything's kind of in the 85 to 95% range. So we feel like the performance is pretty good, and we do get. We've sort of taken this thing from a push rod that you have some feeling for to something that at least is reasonably quantitative and can be used to screen these sites in different applications. So just to sum that up then, this friction sound probe is kind of a new technology that we adopted from some previous work that folks had done. It provides, I think, a nice capability for just rapid in situ mapping and profiling of mean particle size. It enables this rapid ability to kind of get an idea of maybe where contaminated sediment zones are, as well as where preferential groundwater discharge zones might be, and to look at remedies like thin caps or maybe amendments that have different textures to them, and get an idea of if they've been laid down properly, how much mixing is going on, and maybe if they're being affected by things like new deposition. And in the big picture, we just trying to address needs for the DoD to get rapid, less expensive, standardized tools that can be taken to the field and really understand bait and transport at these sites and be able to develop and refine conceptual site models. So with that, I just have this link to the CERTUP ESTCP site where the reports that document the technology can be found, and my contact info. I can also provide info to the folks at ZebraTech who build the equipment. And just wanted to acknowledge the support from CERTUP ESTCP, both for this project and also for hosting the webinar. It's really a great thing. So thanks very much.
Thank you so much, Bart. And we have time for several questions. So the first one has to do with the number of people required to operate your proposed system. Can you please address that?
Oh, yeah. So, yeah, essentially, I mean, it depends a little bit on it. You know, a fair amount of this goes with just boat operations. So outside the boat operations, we typically just have 2 people, one person to kind of handle the frame and the deploying of it, and then one person who's monitoring the data to capture the files. And oftentimes we've been mounting a camera on the thing as well, so that operator is looking at a video camera to make sure that there's not like a giant refrigerator or something underneath it that we're going to try to push the probe through. Great,
thank you. Have you looked at the sound intensity across different frequencies? There's a comment having to do with the intensity alone allows estimating mean particle size, but the intensity across frequency spectrum might enable estimation of particle size distribution, not just mean particle size.
Right. Yeah. So we do have the ability to capture the complete sound spectra, and we haven't delved into that, I don't think, in the level of detail that needs to be done yet, but I do agree that there is the potential to get more information from the spectra that would tell you about different aspects of the grain size distribution. But we haven't pursued that yet to sort of the level that I think is like ready for showtime.
Great, thank you. There are a couple of questions about the impact of free product on the results from the probe. How does the presence of free product or wood chips in the sediments or other compounds impact your results?
Yeah, so I don't think we've had it in a site that had free product. We have, I guess the kind of things we've had some experience with are things like shell hash or aggregate and things like that, where you can get, you get kind of spikiness in the probe as it kind of clanks through some of that stuff, and so you can tell when you're in that kind of a material. It doesn't tell you what the material is per se, but it does tell you that there's something there besides just sort of normal grain type sediments. And I don't know really exactly how it would respond to a free product. That might have a tendency to kind of lubricate the thing and dampen out the sound or something. And wood chips probably have maybe somewhat of their own signature as well. But those would specific materials like that, I think would be things you would want to maybe test in the laboratory to get a sense, if you suspect that at your site, to see if it has a signature that can be distinguished, say, from the background sediments.
Thank you, Bart. How long does it take to make a friction sound probe measurement in the field, and how many stations can be mapped in a day?
Yeah, so I mentioned this a little bit. I think typically the push itself is about a 2-minute operation, and so most of the time is just positioning the boat, getting on the sites you want to get. But we've been doing on the order of you can relatively easily do 5 to 10 stations in an hour, and so you can push through 30, 40 stations in a day. if you're not stopping to do diver collections and things like that alongside of it.
Thank you. What are the known limits for this technology? To what depth is it reliable, and can it be used for mapping mine tailing metals, or is the particle size too irregular?
Okay. Yeah. So, I think the kind of the global limitation right now is just that you're just getting right now we're just capturing and looking at sound intensity. So it's sort of a one-dimensional kind of measurement that is proportional to seems to be reasonably proportional to the mean size. So it's not telling you a lot about the distribution of size, but more about generalities of the mean of the size. So that's really kind of the gist of it right now. The physical limitations right now, the probe we mainly use is a 3-foot probe, and so you're limited to depths of about 3 feet. But you can see from the design of it, and we've already rigged up an ability to go, say, to a 5-foot probe. You're pushing it with this pneumatic cylinder, so to maintain the constant velocity, you need something like that. And that cylinder, as it gets longer, and everything just becomes more cumbersome. So I think pushing things in the 3 to 5 foot range is relatively straightforward. Going beyond that, you probably start looking at a different kind of deployment system. But the probe and the sensor itself is very simple and could be mounted in other kinds of drive systems, for example.
Thank you. What is the effect of sediment consolidation on the response of the system?
Yeah, so that's a good question. So back in the beginning where I said there was some assumptions about about certain things being equal or constant, friction is proportional to the normal force of the particles on the probe. So in general, in kind of unconsolidated sediments, that force is going to be reasonably consistent. As sediments become more consolidated, one of the things you're going to find is that force is going to go up. And so you can get a higher response in consolidated sediments than in unconsolidated sediments. So that's one of the things that we think injects some of the noise we see into the data. And to address that, one of the things we've included, it hasn't really been completely finished yet. I'm just going to show in this backup slide is we've included a measure of push resistance. So by measuring the pressure difference across the pneumatic cylinder, you can measure the push resistance, and that is typically going to give you a way then of maybe normalizing for the consolidation of the sediment, because then something about the forces involved. So this is kind of still in refinement, but provides some way of dealing with the consolidation question.
Great. Thank you, Bart, for an amazing presentation and for taking the time to answer questions. Unfortunately, we are running out of time and will not be able to answer the remaining questions at this time. I guess between you and Phil, you generated so much interest. This is the most we've gotten in terms of questions. So on behalf of CERTUP and ESTCP, I would like to thank you both for sharing your materials with us. And I'd also like to thank our audience for attending today's webinar. I would like to remind everyone that both the presentation and the audio will be archived for future reference on the CERTUP and ESTCP webpage. The next webinar in this CERTUP and ESTCP webinar series is in 2 weeks on December 4th, and it will focus on the roles on efficient tar management and rotary kiln gasification for base camps as options for waste to energy. So the topic is waste to energy, and we're going to have an introduction to the topic by Leigh Knowlton from the U.S. Army, followed by 2 presentations, one from Lockheed Martin and the other one from the Army Engineer Research and Development Center. So you can register for this presentation, for this webinar shortly on the Startup ESTCP website. And I'd like to remind you, so that we can continue to improve this program, to please just take a few moments and to complete the survey that's going to pop out on your screen after the presentation today, just to help us come up with ideas for future topics and to try and address any difficulties that you may have had with this webinar. So again, thank you all for joining us, and we'll call it a wrap. Thank you so much. Bye-bye.